Hello, welcome. We killed some more trees this time. There are 4 handouts, 27, 28, 29, and 30. There's a sample final exam. There are 2 sets of homework solutions, to number 5, which you've already handed yours into, and number 6, which you didn't need to, and then the final set of lecture notes. This is the last week. There will be a bigger than usual review session this Friday, starting at 10 a.m. instead of 11, 10 a.m. to noon, but same place and same day, Skilling 193, and it's broadcast on television, SITN E1, I think it is, and it will be about the final exam and such like things. I understand there was some problem with the computer systems for a few people last night. There's a message on the news group bulletin board that you should read if that affected you, and you can get an extra late day if you were one of the people who was directly affected by whatever it was that happened last night. I'll have a couple more things to say about the final a little bit later. This is Dead Week, and I'm feeling a little philosophical. Permit me to take a couple of minutes to do a little bit of diversion. Remember this gadget I showed the other day? It's the IBM photo chip store with, I don't know, 100 bits of information on this little gadget. This, I suppose, is weakly related to the topic of I.O. and peripheral devices. Stuff has about 100 million bits of information. Each one of these things is about 4 million bits of information. It's made out of a piece of bio non-degradable plastic, laser etched. How long do you think it'll last? Forever. Well, pretty close. It'll probably be 10,000 years, 20,000 years. Even if you put it in a landfill, you probably can't destroy it. So this would be a great place to make archival storage of documents, of things that have to last a long time, right? How do I read this? There are no machines in existence in the world anymore that can read these things. There were 3 of them once, and IBM built them and had an engineer full-time to maintain them. They're certainly not maintained or running anymore. Probably even the information about how to decode this, the algorithms used to encode the information, after all it was complicated, redundant information, error-correcting codes and all of that stuff, is maybe written down somewhere, and maybe you could find those documents, but it would be tough. We've wound up creating a storage medium for information which has great permanence for 10 or 20,000 years, but its longevity in terms of its usefulness as an archival storage is 10 years, something like that. What do we do to solve that problem? What if you were the federal government and IBM had sold you one of these machines and you had recorded on it, let's say, all of the raw data from the 1960 census? How would you get that information now? Well, in fact, the federal government didn't, but they almost had a crisis like that with the 1960 census data, because it was all recorded on magnetic tape of a form that people no longer make tape drives for anymore. And about 5 years ago, in 1990, there was a congressional committee that discovered this and realized that that data was about to disappear unless they did something for it. And they, in fact, read all of the tapes and re-recorded them in a medium that might last for the next 10 years and 20 years, and then they have to worry about it again. We create storage media which have great attributes for our near-term use, but in terms of long-term use, it becomes unusable as quickly as the obsolescence cycle of our technology, which is, as you know, incredibly high. Whereas if you look at some low-technology storage media, like high-quality paper and black ink, you can read a book from 500 years ago and not use any machine and not require any translation, and it's as readable now as it was 500 years ago, and it'll probably be readable 1,000 years from now. So something to think about. What got me started thinking about that actually was an article that appeared in this January's issue of Scientific American that's about this subject and the digital and the longevity of digitally recorded information and what we can do about it and how we can make self-describing information so that even if the machines don't exist, you might be able to figure out the encoding for it 100 years from now. It's certainly a continuing problem. If you think that the CD-ROM with the street atlas of your city is going to be readable in your personal computer 100 years from now, you're mistaken. That information is going to be dead. So all of the books that are currently being published on CD-ROMs have a lifetime of maybe 10 or 20 years, not 500 or 1,000 years. Anyway, end of philosophy. If anybody wants to comment, you're certainly welcome to. But back to the topic at hand, which is I/O and I/O devices. We talked about benchmarking for I/O, and we talked about I/O devices, mostly disks, and various schemes for getting bigger disks and more redundant disks. And we went over a problem that shows how to do some kinds of performance analysis for I/O systems. What I'd like to talk about now is the relationship between I/O and the CPU, and how is it that they talk to each other and interact with each other. And that leads to the subject of buses. Now, back in the old days, computers didn't need buses. You built a special purpose attachment from whatever your I/O device was to whatever your CPU was, and you maybe even built a special instruction to handle it. So a computer had a teletype, and there was an instruction that says write character to teletype, and there was a direct wire that connected the teletype to the computer. No need for buses. Now, obviously, in a much more general computer, you need a way of attaching multiple devices, and you need a way of replacing devices and attaching different kinds of devices in a uniform way somehow to the computer. In fact, we wind up, as with cache is a hierarchy of memory systems, here we wind up with a hierarchy of I/O buses, where the buses close to the processor tend to be the ones that are fast and small and special purpose, and the ones that are farther away tend to be bigger and slower and general purpose. The fastest and smallest and closest to the processor is the processor memory bus, and typically it has only memory on it, although it may have special purpose memory these days, like memory used for display controllers. You want to have the highest possible bandwidth between the processor and the memory, something like 250 megabits per second. And because of the electrical characteristics of a bus like that, it's required that it be short, and there be all sorts of restrictions on how it is that you can plug devices into it for various electrical reasons, including reflections and propagation delays and time considerations and so forth. This is one of the places where processor designers get to innovate, because those processor memory buses are often proprietary, and you can't just plug any old thing onto it. You can only plug special purpose processors or special memory cards onto the bus. And this bus is often restricted to be on the printed circuit board that the processor and its near-term memory are located. And this memory is typically the second-level cache. The processor might have a first-level cache, this is a second-level cache, and then the bulk of main memory is elsewhere. These buses tend to be synchronous for highest speeds, and we'll talk later about what that really means, but it means that it's clocked at a constant rate with no chance for the memory to say, wait, I'm busy. The processor just says, give me what you got, or here's my data. The next stage away from the processor are the backplane buses. These are the buses into which you plug other bulk memory cards or I/O cards directly, or I/O controllers, so that you plug in I/O devices indirectly. These tend to have moderate speeds in the order of 50 megabytes per second, something like that. They can be either synchronous or asynchronous, or both. There are some buses defined that allow either synchronous or asynchronous transmissions. They tend to be longer, but still limited to how much you can put in a box, like 18 inches or 2 feet or 1 foot or something like that. And it's standardized. And as you can see, the wonderful thing about standards is that there are so many of them to choose from. All of these are standardized to one degree or another, sometimes by official standardization agencies like IEEE or ANSI, and sometimes just by convention, by the fact that lots of manufacturers build things to those standards. And they come and go, and the lifetime for these standards tends to be about 10 years, maybe 15 years if you're lucky, and then the bus is too slow and gets replaced by something which is faster. The buses that are used for PCs these days, the IBM-style PCs, are these buses, the old industry standard bus, IBM's attempt at making that sort of non-engineered bus faster, and then everybody else's attempt to make that non-engineered bus faster, neither of which have been great successes. And in fact, the old hacked together bus tends to be the one that is used more than anything else. This PCMCIA is the credit card adapters. Small, especially portable computers are using these plug-in things that look like credit cards for memory and devices and so forth. And this is the standard. This stands for Personal Computer Memory Card Industry Association or something like that. It's a ridiculous acronym, but it's the credit card size thing. And so forth. The next stage out are the I/O buses, which tend to be slower. They are longer, and they're typically outside or allowed to be outside of the box that actually makes up the computer, and have cables that can drape from one side of the room to the other, limited by a distance of 5 or 10 meters, something like that. The one that gets most of the play these days is probably SCSI, used for connecting disks and tapes and CD-ROM drivers and so forth. IBM I/O channels for mainframes were exactly the same sort of thing, and for years set the standard for how it is that devices ought to be connected. And by publishing that de facto standard, it never was blessed by any of the official agencies, IBM created an entire industry of so-called PCM, plug-compatible manufacturers, that would make tape drives and disk drives that would plug directly into IBM systems using the interface that IBM had defined for their I/O channel. Ran at the same speed of 3 megabytes per second for probably 15 years, yet IBM mainframes, even with a channel that was relatively slow by current technology, set the standard for mainframes with high-performance I/O systems because of the way their channels worked and the multiplicity of channels that could be connected. Okay, I talked about, or mentioned at least, synchronous versus asynchronous buses. You should at least have an intuitive feeling for what the differences are between them. A synchronous bus is a bus where there is a fixed clock that runs at a constant rate, and whenever whoever is putting data on the bus wants to send something, he puts that data on the bus in a certain relationship to that clock and expects the guy at the other end to sample the data, to read the data off with some relationship to the clock. So for example, a CPU might decide that on the rising edge of the clock, it's allowed to change the address and data. Remember, this bus has a whole bunch of address lines, a whole bunch of data lines, and then a few control lines, one of which is the clock. And there tend to be fewer for synchronous buses than for asynchronous buses. So the CPU puts all the addresses on, puts all the data lines on, the clock rises, and then sometime later, the device at the other end of this bus gets to sample the data. Well, how fast can you do that? Well, remember that you've got one device sending data, and it's sending all of the address lines, and the propagation speed of that information is basically the propagation speed along the bus, something close to the speed of light. The problem is that there are multiple signals that are making their way down to the bus to the device at the other end at the same time, and they may not be going at exactly the same rate. The rate is not exactly the speed of light. It's less than that for one thing, and it also varies depending on conditions of the lines on the bus and what other devices are attached in intermediate places and so forth. And we talked about this for pipeline clocking as well. That's called clock skew, and the difference in arrival time between two different signals that the CPU sent to a device is the clock skew. And basically, the device has to wait a time which is at least bigger than that clock skew to make sure that it's got a consistent set of signals all arriving at itself at the same time. So basically, the maximum rate at which you can clock a synchronous bus is proportional to just the clock skew. Notice that it's not necessarily proportional to the propagation delay. As long as all of the signals will get there within a clock skew time, the CPU, in fact, could, in a kind of wave pipelining sense, send out multiple waves of these changes to signals. People tend not to make wave pipeline backplanes because they have other problems, but in theory it's possible. But the nice thing about synchronous buses is that it's fast, because the cycle time is related only to one clock skew time. The disadvantage is that there's no feedback mechanism here. The CPU or whoever's driving data on the bus sends out its information. It has no idea whether the device got it. It has no idea whether the device is ready for it. Sometimes, if that's a problem, you can patch it up by allowing wait states. So you could have some clock cycles where the CPU does nothing because it knows that this device is slow and is going to take a while to respond to the bus. But it's sort of dead reckoning. The master on the bus, the CPU sending the data, has to know in advance how that device is going to react to the data that it's sending down at the other end of this corridor. The alternative to that is an asynchronous bus, which has no clock that keeps going at a constant rate, necessarily, but rather waits for handshaking from the other end, so that the CPU doesn't go ahead until the device has acknowledged that it's gotten the data. This allows you to use devices of varying speed, and depending on how fast it is, it will respond sooner or later. But in general, it's a much slower bus, and here's why. Let's look at the CPU putting address and data on the bus. Then it raises a request line, and it has to wait for the response back from the other guy before it lowers its request line. So what happens? Well, it raises its request line. That request propagates down to the other device. When it sees it, it raises its acknowledge line. So that's one propagation delay across the bus. Then that acknowledge line has to propagate back. I mean, remember, these are two devices, the CPU and the device. The request line is going out. The ACK line is coming back. So that's two propagation delays before the CPU sees the ACK and can lower its request line. And then you've got to get back into the initial state. So the device has to see the request line going down before it lowers its ACK line. And the CPU has to see the ACK line going down before it's ready to do the next request. So the whole cycle time is slowed, has to be as slow as at least 4 times now the propagation delay across the bus, in worst case, from one end to the other, plus another factor that has to do with the skew, the relative rates at which signals arrive. Now, the actual points in this cycle at which the data changes and the remote devices actually samples the data, and if in the case of a read from the device to the CPU, the point at which the device provides its data varies from bus to bus, and all of the bus standards do things slightly differently. But the common element is that asynchronous buses tend to be slower because they have 2 or more commonly 4 times propagation delays in the fundamental cycle for every transaction. But the advantage is that it works with devices of variable speeds. Any questions about that? Now, I've been talking mostly about CPUs as the devices which are sending and receiving data on the bus, but that's not necessarily the case. There can be, for one thing, multiple CPUs in a multiprocessor environment. There can be I/O devices which look like independent suppliers of information. You've got a network adapter, for example, which suddenly receives a packet and needs to send information to the memory, for example, or send something to the CPU. Once you've got a scheme like that, where there are multiple masters, you've got to have some scheme for deciding who it is control of the bus and who it is that is initiating transactions on the bus. And that's the scheme for bus arbitration, basically deciding who goes first. And there are lots of different schemes for doing that. One is a central arbiter. If this is the bus, you can have a kind of private communication between each of these devices and some piece of centralized logic that decides who it is gets to go on the bus next. So anybody who wants the bus to be able to send information to memory, for example, memories tend to be passive on the bus, raises a signal to the arbiter and waits until the grant line comes back saying, you're the guy who now has it. And anyone else who raises the request line doesn't get a grant line until that bus transaction is over. This is nice. It allows the arbiter to be clever in all sorts of ways. It allows it to be fair, if it wants to, in parceling out bus time to these devices. It allows it to impose priorities, if that's important, so that device 2, which is a high priority disk transfer, for example, might go ahead of somebody which is doing a tape or a network transfer or something like that. The problem is it doesn't scale very well, because it works well in a picture like this that has 3 devices, but if I have 10 devices or 16 devices or 100 devices, the arbiter has to get increasingly more complicated as I add additional devices. and the wiring between devices and arbiters begins to get more complicated. So another way of doing this, which solves that problem and is sort of infinitely extendable, is a kind of daisy chain approach, where you add to the bus on which transactions are actually going another line that goes back to a single arbiter. Now again, we have an arbiter, but this arbiter is a piece of fixed logic that doesn't depend on the number of devices. And that single fixed line says that somebody is requesting the bus. Please grant it. When that happens and the bus is not busy, he generates a grant signal. And that grant signal gets propagated down from device to device in daisy chain fashion, each device deciding whether it's the one that wants the bus, or in general, does it want the bus. And if so, it blocks the grant from going on further down the chain to the next devices, and then accesses the bus. And when it's finished, it releases that block. A way that one might consider implementing that logic is something like this. Let's say that this is a device, and I've got the grant signal coming in, and I want to generate a grant signal coming out. And I've got a piece of logic inside that says, I am requesting the bus. You know, I'm a disk, and my seek is done, and I want to do a data transfer. So you could have some logic that says that, well, if I'm not requesting the bus, and the bus is being granted to somebody, this is meant to be an AND gate, then forward the grant on to the next guy. But if I'm requesting the bus, then this becomes a 0. You don't forward the grant on to the next guy. But if the grant comes, then I get to go. So if I am requesting the bus, and if there's a grant line coming into me, then I generate my go signal that says I get to use the bus, and the bus is sitting down here someplace. That's roughly speaking how logic like this works, but there are all kinds of complications. This, as drawn, don't build it, won't work. For example, what happens if yes, okay, well, consider the following case. Consider the case where I'm not making a request, so the grant line is being propagated through me to somebody else who is in fact using the bus. And then suddenly I get some event that occurs that says that I ought to get the bus. Well, I raise my request line, and suddenly I've just canceled the next guy's grant, although it may be in the middle of his bus cycle. Because my request line went on, I suddenly disconnect this, causing the grant line not to propagate down to the next guy in the sequence. I generate my own internal go signal, but in fact it's the middle of somebody else's bus cycle, so that won't work. So one way to solve that problem is that you might want to use edge triggering. You might want to say that you make this decision once on the rising edge of the grant line, and then you wait for the grant line to disappear, and on the next rising edge of the grant line you get to make your decision about whether or not you get to go, whether you get to acquire the bus. Well, that works, and it solves this problem, and it makes it a correct solution. It still doesn't have a fairness property, because if you're a guy that keeps making requests over and over again, and you're at the head of the string, every time the grant line comes through, you're going to grab it and go, and all of the devices downstream of you will not get any permission to get access to the bus. You can fix that too in daisy train schemes. You could, for example, remember that everybody is driving the request line with the request signal. After you are issued a grant and get your access to the bus, you can decide that you're not going to issue another request until you see that the request line has gone back up, which means that everybody downstream of you that has made a request has had an opportunity to have his bus request satisfied. So there are schemes for, number one, making daisy chain arbitration correct, and number two, for making them even more complicated with priority schemes or fairness schemes or round-robin schemes. There are other schemes where, in addition to grant signals, you might want to send down a priority signal that says whether or not I'm the highest priority on the bus or the next guy is the highest priority. So you can have a kind of rotating token that says who it is the highest priority device on the bus. And people have elaborated daisy-chained arbitration schemes in lots of different ways. They begin, in fact, to look very much like networks, and we'll talk later on about networks and arbitration and allocation of bus bandwidth to networks, solving the same kinds of problems and in the same kinds of distributed ways. Speaking of distributed ways of solving the bus arbitration problem, another way to do it is a way, in fact, where there is no centralized logic at all. There is a completely distributed kind of logic. Typically requires multiple lines, and one simple way to do it is that every device has a private line on the bus that says, I want the bus, and he drives his private line when he wants it, and then watches all of the other lines for all of the other devices, seeing whether anybody else wants the bus at the same time. If nobody does, and he's the only one that wants it, then he gets it. If multiple people want it, and each device sees that multiple people wants it, then there has to be some other kind of, another policy for deciding who gets it, and it might be a priority policy that says the guy with the top line currently requesting the bus is the one that gets access to the bus. SCSI uses a scheme like this with in fact 8 wires, so there can be 8 devices on the bus that are making requests in a distributed fashion for control of the bus. Its advantage is you don't need any central control at all. Here you needed a central control whose size was proportional to the size of the devices. Here you needed central control, but it was independent of the, not the size of the devices, but the number of devices. Here it's independent of the number of devices, and here you don't need any central control at all. It's completely distributed.
Question?
Yeah.
What if there's more devices, though, than there are lines on that? You said each one of them had a dedicated line on the bus.
In that case, you're in trouble, and that's why SCSI, for example, is limited to 8 devices on the bus. That doesn't scale very well. There are other schemes for binary encoding the address of the guy requesting it on the bus that gives you an extra power of 2. So with 8 lines, you could, in fact, get 256 devices, but that's a little more complicated. Okay, how do you make buses go faster? Now that we've made them work, our interest is always in making them go faster, and here are some of the techniques. Well, one thing, as I pointed out, is you make them synchronous instead of asynchronous. That, in general, makes them go faster, but has the disadvantages I described. You can always make them wider, and then in a single bus cycle, if you've made it twice as wide, you transmit twice as many bits per cycle. Obviously, the expense gets larger. The physical constraints sometimes make this not possible, like in the credit card adapters, the PCMCIA cards. You can't make the bus very wide because the connector is too small. Another issue in how fast the bus goes is whether there are separate lines on the bus for data and addresses. Now, in the case of reads, it doesn't really matter because you send out an address to memory, and then sometime later it sends back the data to you. And you can use the same wires for address and data because they're not used in the same time. But if you're doing writes, and if you have separate lines on the bus for data and addresses, then you can get the writes to go faster. Because in one transaction, you put the data and the addresses on simultaneously, you do whatever clocking you need, and the thing is over. You don't have to separately put data and addresses. This should be reminiscent of the design for RAMs, where you might, in fact, want to multiplex data and addresses, or addresses and addresses into multiple parts, and trade off speed for a number of lines. Another thing you might want to do is split transactions. We've always been talking in terms of doing one individual operation on the bus, like reading from memory or writing to the disk. You may well want to split those into 2 separate parts, a request and a response. For one thing, if you're talking to a device that takes a long time, like reading a block from the disk where it might do a seek, you want to free up the bus to allow other people to use it in the meantime. So you send out the request, you end that transaction, give up the bus to somebody else, and then wait for a response to come back sometimes later. You might even want to do this for RAMs, especially, or for memory in general, especially if it's a memory hierarchy, where depending on the sequence of cache misses, the memory read might take a while. So you send out a request on the bus that says read a piece of data, and you get a response back sometime later that says data is here. There are hybrid schemes where you send out a request and you get a response saying, here's the data, in the case where it was in the cache, or you might get a response saying, the data's not ready yet, wait for me to get to you later. in which case the bus is freed up, and then sometime later another command from the memory device comes saying that I've finally got your data and here it is. Now notice that once you've done this kind of split transaction, you've got a problem. Allows a sort of a polite way of saying it. It really now requires some kind of queuing or pipelining of these transactions, because if there are multiple requesters on the bus, then multiple requests might be sent to the same device to do a memory read or a disk read or something like that. And now suddenly the entire system is more complicated because there either has to be some mechanism of queuing or pipelining these transactions, or some way of saying, I'm busy with a previous transaction, please go away and come back later. So split transaction buses tend to get much more complicated. Split transaction buses, though, tend to be more and more common, especially for the longer buses, for the I/O-like buses, for the SCSI buses, and certainly as buses begin to transform themselves into networks, and we'll see how that happens later, split transactions are almost a requirement. Another way to make it go faster is that we spent this overhead in arbitrating for the bus and fighting for everybody else who wants that bus. Once we've got it, why not pay that overhead once and transfer a whole bunch of words rather than doing it for a single word? In fact, this is done a lot, especially for disk transfers, where you might want to transfer an entire sector or a part of a sector or 16 bytes at a time or some larger block than a single word on a single bus transaction. So the bus transaction is an initial phase followed by multiple data phases. Another way to make it go faster, let's skip multiple bus transactions for a second, is to split a single bus into multiple independent buses. For example, if we have a memory device and a CPU and an I/O device on it, you may choose, in order to get essentially double the bandwidth, assuming the memory can sustain it, to split other I/O devices, like, for example, a video driver, onto a separate bus, so that the video and the memory, or the audio for multimedia computers, can be transferring data in and out of the memory without affecting the reference of CPU to memory or of CPU to other I/O devices, basically by breaking that connection and creating multiple independent buses. Sometimes, in fact, you can have a breakable connection there that allows, with greater latency, the CPU to get access to these other devices, but most of the time these buses are independent. Sometimes you allow them to link and do a common transaction, but most of the time they're independent to do independent transactions. Another way is to split up transactions into different phases that allow you, in a sense, to pipeline transactions and allow multiples of them to be on the bus at the same time in different phases. For example, you might like to pipeline the arbitration part of getting on the bus with the data transfer part of the bus, so that while one pair of devices is transferring data to each other on the bus, at that same time, the next pair of devices that want to talk on the bus is arbitrating for control, trying to decide who of the many people wanting the bus is going to get it. So you do an arbitration phase while data is in progress that controls the data for the next cycle. So you've essentially done CPU-style pipelining for the bus, getting it to go faster. Okay, how is it in general that CPU controls I/O devices? Once it gets on the bus, it talks to that I/O device. What is it saying? There are two basic ways of doing that. Certainly the easiest way is for the CPU to directly control the I/O device. And you see two different ways that this tends to be done. One is by having special instructions in the CPU that are there for I/O control, that are there for inputting and outputting. There might be an input instruction or an output instruction. The x86 family has that kind of architecture. really, these are just a special form of memory load and stores, and the processor knows that they're directed to I/O devices, so it may treat them slightly differently. It may expect the timing to be different than it is for normal load and store instructions. But really, people have observed that there's not much difference between input and output instructions and load and store, which are input and output instructions to a memory device. So in fact, most later processors tend not to have separate instructions for that, but simply treat I/O and I/O devices as special magic locations in memory. And when you reference those magic locations, it doesn't read or write into memory, but it reads or writes something in the I/O device. It might be a command register that tells the I/O device what to do, or it might be a status register that the CPU is reading that tells the CPU whether a previous operation is finished, or whether the device is free, and so forth. But here the CPU is in direct control of the I/O devices. Another way to make things happen in parallel is to allow the I/O devices to be controlled by separate computers, if you will, separate channels or I/O processors that are independent controllers of I/O devices and manage the transfer of data to and from the I/O device. That leads into another dichotomy that I should discuss first, which is how it is that the data transfer really is done. For some slow-speed devices and older computers, the transfer from an I/O device to memory is done by way of the CPU. So the I/O device itself is not a bus master. It's not one of these things that can arbitrate for the bus and store data directly into the memory. All it can do is respond to commands from the CPU, one of these kinds of commands that say read data or write data. So every transfer from those I/O devices to memory requires mediation by the CPU that does the read from the I/O device and then the store into memory. Obviously, a much more efficient way to do that is to do direct memory access. This is the so-called multiple master case, where I/O devices as well as the CPU are allowed to be masters on the bus and are allowed to do transfers directly in and out of main memory. And there have been a hierarchy of schemes going from simple CPU-oriented I/O transfers to what amount to entirely separate computers that do the I/O transfer. An example of the sort of simple CPU-related, CPU-controlled I/O is kind of an old-style Z80 microprocessor. The next step up is the kind of DMA access that we've been talking about, and all the current microprocessor systems allow I/O devices to do that. The next step up from that is, in fact, to generalize this DMA to be something which is almost a computer. IBM-style channels were like that for the IBM machines. And in fact, they executed a little program, and each channel command was an opcode of a few bits followed by an address which represented the data to be transferred. And in fact, there was even an opcode which was a branch instruction that allowed the channel to execute this little program that directed the flow of data to and from, between a device and memory. The next step up from that is to make the channel into a complete I/O processor and make it a completely independent computer that is separately programmed with an instruction set that's probably different from the main memory because it's tailored for its function as an I/O processor. And well, one machine that comes to mind, one old machine that comes to mind that did this was the CDC 6600 that had a single central processor unit and 10 I/O peripheral processors whose function was only to do transfers between I/O devices and main memory. So that's the spectrum of how transfers are done. Then the question is, how does the CPU know when this is finished? Obviously the CPU, if it's any one of these schemes, is off doing something else while the transfer is in progress. One thing it could do is just poll. It can just hang around waiting, checking the status register, doing one of these memory mapped I/O or separate I/O instructions, waiting for the device to say that it's done. Well, that's kind of dumb because the CPU is not doing anything. It might as well be doing the transfer itself if you were going to do that. So obviously the thing to do is to have interrupts and to allow the CPU to continue executing and then get an interrupt when the device is finished. But of course there are multiple devices that may be executing at once, so there needs to be some scheme for deciding when the CPU gets interrupted which device is it that has finished its operation and needs to be serviced now. There can be one interrupt, in which case the CPU gets interrupted and has to look around at each device one at a time to see which has finished and which to service. Or the devices can notify the CPU somehow on the bus by putting their ID when they raise the interrupt line that says, I'm the device that interrupted. And that can either send the CPU to different locations, different interrupt routines, depending on which device is interrupting, or it can go to one interrupt routine and the CPU can read some kind of a register that says which device caused that interrupt. Notice now, though, we have an arbitration problem of the kind that we've seen now 2 or 3 times before. We now have simultaneous interrupts. We have to deal with the fact that if they occur at the same time, we've got to somehow prioritize or control which one of those interrupts is going to occur, especially in the case where interrupts are vectored, where there's a bunch of lines on the bus that the interrupting device uses to tell the CPU who it is. If there are multiple of those devices, then somehow they've got to now arbitrate for placing their device ID on the bus. And the same kinds of schemes that we used for arbitrating for the main bus can be used to arbitrate for among devices when simultaneous interrupts occur. Question? Okay, last issue in I.O., and this is really has been a sort of high-level overview of I.O. in computer systems, is what to do about interactions between the memory hierarchy and the I.O. And actually, I think we've talked about this mostly before. There are 2 main problems. One is that there are caches, and depending on where you connect the I.O. system in the memory hierarchy, you may or may not have a problem with cache data. Now, the best thing to do, if you're willing to pay the penalty, is to have the CPU, which is, after all, talking to a cache, which is talking to main memory someplace. If you make I.O. devices look just like the CPU and go through the cache first before going to main memory, then you don't have any problems, because whatever the CPU sees, the I.O. device sees, and it always sees up-to-date information. The problem is that's very inefficient, because for one thing, I.O. is going to be invalidating cache lines in the cache when it's reading or writing, and those lines will probably be never used again because they're off getting streamed to a disk or a tape or something like that. In the meantime, throwing out lines that the CPU might want to be referencing. More serious problem is that the CPU and the cache are, in fact, at least the level 1 cache, probably inside the same chip. And now, instead of having I.O. separately done outside on the processor to memory bus or on the back plane bus, you've got I.O. connected through a trap door into the CPU, which doesn't work at all. It's much too hard to do. It takes up too much bandwidth from the cache. So it's more common, in fact, for I.O. to go further down in the hierarchy into main memory, in which case you've got to worry about stale data. And there are several things you can do. One is you can decide to instruct the caching system not to cache whatever pages are currently being transferred to or from using I.O. The other thing you can do is that as transactions are going on between I.O. and memory, you can have the cache monitor them, not get involved if it doesn't have any of the data or doesn't need any of the data, but checking the tags in the main memory based on the I.O. transfers, and if they match, then do something appropriate. If the I.O. is storing something into memory that also happens to be cached in the CPU, the cache can notice that and invalidate the line that it currently has in the CPU, in the CPU's cache. So the next time the CPU needs it, it goes to main memory. So these kinds of schemes are required in order to get the appropriate data to be transferred to and from I.O. and to and from the CPU. So the other problem we talked about is that the I.O. and the CPU may not be using the same addresses. Remember that the CPU is translating, let's say using a translation look-aside buffer, virtual addresses to real addresses. There's a cache involved here too, maybe before, after, or on the side of the TLB as we discussed. And then it's going to the bus on which main memory sits. Well, the I.O. device may or may not be using virtual addresses. It's talking to some DMA controller that's trying to go directly to memory. The user process, the CPU, is typically using virtual addresses to instruct the DMA. But the DMA now is not going through the translation process, so it is going, unless you fix it, will be going to the wrong addresses. So what can you do? Well, one thing you can do is translate virtual addresses to real addresses in software before you give it to the I.O. In fact, IBM mainframes did that. Those channel programs that I was describing operate only on real addresses. When the CPU creates a channel program, it's got to manually do what the translation look-aside buffer normally does automatically and translate the virtual addresses to real addresses in order to give to the I.O. That works. It still has the problem that the pages in real memory may not be contiguous. So if you've got a process in virtual memory that asks to read a disk block into this area of virtual memory, that area may in fact be split into two separate real memory blocks. And there's no way of translating this sequence of virtual addresses into a channel program for the DMA device, which breaks it into two separate sections. Well, I say there's no way. In fact, there is a way. You wind up making two separate transfers in the DMA controller, one for the first part in this real memory location, one for the second part in this real memory location. And in the IBM mainframes, they did exactly that. They translated a single data transfer into perhaps multiple of those channel commands in order to break it up into the physical real memory blocks that are in memory. An alternative to do that is to give the DMA controller, in fact, its own kind of TLB. It doesn't really have to be TLB in all the complexity of the CPU TLB, because it's probably only mapping a very small area, but some kind of a translation box that does a virtual to real translate. And in that case, you can give the channel or the DMA controller the same virtual addresses that the CPU is referencing and have it translate on the fly. Now, you've obviously got to keep track of this, the operating system does, and to change it as pages move around, and to change it as processes change within the CPU. But it's a scheme that works well. Any questions? We are at the end of I.O. And we've got about a class and a half left. Now, what I'd like to do for the rest of that class and a half is kind of do a quick overview of multiprocessors and networks in one class and a half, each one of which could certainly be a course in itself. So obviously we're not going to do a thorough job of any of that. But rather than do a very high-level overview, I'm going to sort of do, I guess pilots call this touch and goes, right? When you land the plane and you hit the ground and then you take off right away, for practicing landings and takeoffs. Where we'll be talking about some things that are fairly general, but then we'll dive down into some really nitty-gritty details to give you the flavor of how these things work, in particular multiprocessors when there are multiple caches, and networks when the networks are trying to access memories that are far apart and may be updated at different times. I think it's misleading sometimes if you look only at the top-level overview of those things and don't at least get some view of how the ultimate underlying details might work. What really are the commands that get sent back and forth. So we'll be doing this sort of scattered high-level, low-level investigation of some of these topics. Obviously, we're not going to be doing this in the same depth that we've covered, pipelining and caches and so forth. So by and large, the information, the material I'm going to cover from now on is not going to be on the final, at least not in the form of problems that have to be solved involving this material. Just to encourage you to come, if you, there might be a short answer or two question on the final that is related to this material, but it won't be covered in any great depth. For more about the final, I encourage you all to come to or watch on TV the review session, again, this Friday from 10 to 12. And there's also, remember, the example final, which we handed out today, which also includes the solutions to that example final. So you get a chance to practice.
Will the review session be taped?
Yes, the review session will be taped, and the tapes will be in the library. The final is as originally scheduled, Tuesday, March 21st, 3:30 to 6:30. It will be here, but we've also got the overflow rooms upstairs, 191 and 192. So there should be plenty of room for people to spread out and get alternate seats and obey the honor code and do all that kind of good stuff. Any other mechanical questions? Logistical questions? Okay, let's talk about more than one computer. Most of what we've talked about so far has been how do you build one computer which is as fast as your customer is willing to pay for. Now the question is, how do you connect together multiples of these computers to do something cooperatively? And there's a whole spectrum of how closely you connect them together and how cooperative they really are. The first way to do it is to connect them together very tightly. Basically, you've constructed one computer out of multiple processors that are all in the same box or pretty close to it, sharing the same memories, sharing the same I/O devices, and are in bed with each other, so to speak. A simpler way to do that is the so-called symmetric multiprocessors. You just take 2 or 3 or 4 of these processors, stick them on the same bus with the same memory. They're symmetric because they all look exactly the same. It's not like a CPU and I/O processors. They're all CPUs. And they all sort of work together. It's a great solution for servers. Each multiprocessor can be executing a different task. Obviously, there are lots of problems with synchronization that we'll talk about later. But it works great. It's becoming more and more popular. It was done as long ago as 20 years ago. I would predict that probably within 5 or 10 years, almost every computer you buy will be some form of symmetric multiprocessor. If it's more than a trivial machine. Another approach is to make a massively parallel processor. That instead of putting 2 or 4 or 6 of these things together, put 1,000 of these things together and get them all working together on one big problem or on separate problems if you can figure out how to use 1,000 processors on separate problems. 30 years ago, Mike Flynn tried to characterize the different ways in which 1,000 processors might work together on a problem. And he characterized it in 2 ways. One is, are they all executing the same instructions or are they executing different instructions? That's the single versus multiple instructions. So that's the SI versus MI part of these acronyms. And the other question is, are they all working on the same data or are they working on different pieces of data? Now, obviously, the single processors that we've been talking about are the SISD. We've got one single instruction stream and we've got one single piece of data that we're working on. A style of machine that for a while in the 60s and 70s was popular for people to talk about and build were the single instruction multiple data machines, the kind of array processors, where you've got, the famous one was the Iliac 4, which was, I guess in its last home was over here at NASA Ames in Moffett Field, where you've got, in that case, 64, but it could have been 64,000 processors, all executing in lockstep, all executing the same instruction stream. You send one add instruction to all 64,000 processors, they all execute an add, but they all execute it on different data. So if you're trying to add 2 arrays, for example, 2 matrices together, you issue one add instruction, you've got 64 processors, each adding the 2 elements of the array, of its private 2 elements of the array together. So you've got multiple data operating in a single instruction. Now obviously you begin to elaborate the kinds of instructions that can be executed, because depending on the data, they may want to do different things. So how do you do something that says, well, if B is not equal to 0, then A divided by B? If they're all executing the same instruction, you can't quite do that. Well, what they wound up doing is very much like the conditional execution instructions we saw for some of the pipeline processors. You have a single instruction that says, if B is not 0, then A divided by B. And you issue that to all of the processors at once. They all do slightly different things depending on what data they have. People still talk and maybe build SIMD machines, but they're not quite in as much favor as they used to be. The other extreme is what people are focusing on these days, which is multiple instruction, multiple data. Bunches of independent processors, each executing a separate program on separate data. Now, when I say a separate program, they may actually be executing the same program, but they may be at different places in the execution of that program. Or they may be executing entirely different programs. In the case of a server executing different programs on behalf of different clients would be an example of that. One which is harder to understand an example of is multiple instruction single data. Where can you have 64,000 computers, each executing different instruction streams, but all operating on the same data? I've never quite been able to, I've never seen a good example of that kind of structure. I don't think anybody's built something like that. The thing which comes to mind which is closest is something like cracking an encryption key. If you look at DES encryption, for example, it's possible with current technology to build a multiprocessor that decodes the key by trying all possible combinations. Well, in that case, you might consider that you've got all the processors working, trying different keys on the same piece of data. But it's a stretch.
Wouldn't an example of that be any place where you have shared memory with a bunch of processors on it? I mean, maybe they're not all operating simultaneously on the same little piece of memory, but in general they're accessing the same data.
I suppose you could interpret it that way, but mostly people tend to look at those machines and say that they're actually MIMD because they're most of the time operating on different pieces of data rather than the same data. It's angels on the head of a pin kind of argument, I suppose. Okay, the next step out is, well, that was trying to build a computer which basically fits in a box or in a big box or is close together, a bunch of little boxes. The next step is build a computer which can span a room or span a department or span the floor of a building. And that's what LANs are all about. Now suddenly things are slower, but they're still fast. The interconnections might take on the order of a millisecond or less than a millisecond. And this is the scheme which you're all intimately familiar with doing the kind of client-server computing. Buzzwords these days for a similar kind of cooperative computing over a local area network is networks of workstations, where in fact you borrow CPU cycles for workstations that are underutilized to work on problems that really are somebody else's. In fact, this happens all the time in Sweet Hall, right? You can be sitting in front of, lane 27 doing your problem while I'm dialing in from my home ISDN line and using the spare cycles in the back of your machine at the same time. In a way, that's a network of workstations. Another buzzword people have used is a local area multiprocessor, basically building one of these kind of multiprocessors out of connections which are a little bit slower and go over longer distances, so they can be separated geographically. The next step out is the internet kinds of things, wide area networks, looser interconnects. The time delays, certainly the latencies, probably also the bandwidths, tend to be much longer, multiple milliseconds, but this is the way ATM machines work. It's the way cooperative computing is done over the internet. It was a lot of the original motivation, in fact, for the internet when it was the ARPANET back in the late 60s. The idea was, in fact, to be able to build a multiprocessor out of computers that were linked with these wide area network links, but could all be operating on the same problem, or at least sharing parts of the same problem at the same time. It was especially attractive in the days when there weren't too many supercomputers, and there was one out in Argonne National Labs or Lawrence Livermore that lots of people wanted to have access to, and to connect to their own computers to do cooperative computing, do it over the wide area network. There are lots of ways to characterize these various connection schemes for putting computers together. One, obviously, is the distance. Multiprocessors are less than 10 meters, say. LANs are limited to a kilometer or a mile, and WANs are limited to the size of the planet, or maybe even more. The other major issue is what is the interconnection pattern, how it is that you connect together these devices. Well, a bus is one, and we've talked about that for backplane interconnect, for doing these closely linked processors. Ethernet is an example of using that same topology, at least the original Ethernet, for local area networks instead. Rings are used for all three kinds of interconnects. They tend more to be used for local area networks than others, and token ring is an example of that. But SCI is an interconnect that sort of spans the distance between a local area network and a tightly coupled microprocessor. And it does rings as well, or at least one of its instantiations does rings. Especially for the tightly coupled microprocessors, you can have grids. You can have a two-dimensional grid where each intersection of these communication paths represents a processor, and a processor can talk to any of its 4 neighbors, or any of its 8 neighbors, or its neighbor on the other side of the array, but not arbitrary neighbors. Those are kind of multi-dimensional toruses where these things bend around to each other in 2 dimensions. Or you can do these things in n dimensions. You can consider a 3-dimensional cube or a 4-dimensional cube where each processor can talk to 2 to the nth of its neighbors, but still not everybody. If you're willing to pay the bucks, you can in fact have full interconnect, where you've got n processors, and each of the n processors can talk to each of the other n-1 processors. You spend a lot of money on interconnect, but then you get very low latency and high bandwidth transfers between processors. And people have built especially MPPs, the tightly coupled multiprocessors, using all conceivable combinations of these kinds of interconnects. Especially for wide area kinds of networks, or things that are almost wide area, people are beginning less and less to constrain the topology of the interconnect. You view this thing as a big cloud that somehow has some combination of these interconnection devices or rings or buses, and your devices are connected to them in some fashion, where what you standardize is the interconnect between the device and the cloud, and you may standardize the interconnect between switching nodes inside the cloud, but you don't constrain the details of the interconnection pattern. And these are the so-called arbitrary switching fabric topologies like ATM. This is not automatic teller machine, by the way. This is asynchronous transfer mode, which we'll talk about more later. That is one of the hot new techniques for both doing local and wide area networks. So now we have a way of one computer talking to another. One of the questions you need to ask is, what state information does this interconnect fabric maintain? What does it know about 2 computers talking to each other? If it knows that there is a path set up between them, or if in fact the end nodes know that there's a path set up between them, that's the so-called connection-oriented approach, where there's some state information that keeps track of what the progress of this conversation is, that there are multiple packets that may be sent in opposite directions between these 2 nodes. And you've got to keep track of the sequence of them, of where in this transaction they are. Another approach, at least as far as the switching fabric is concerned, is to use connectionless interconnect, where all you know is that there is a packet that needs to get from station A to station B, and when it's over, you can forget everything you ever knew about that packet and the 2 stations that are doing transmission. There's no state information maintained by the network itself. If the packet went wrong, it's not your fault, or it's not your problem at least, it's somebody else's problem. And that's the connectionless scheme, which tends to, well, there are complicated trade-offs between the 2 of them, but the connectionless schemes in general tend to be much simpler for the switching fabric, more complicated for the nodes at the ends that have to deal with the fact that the switching fabric is not keeping any state information for them. Another issue is flow control. can station A, if it's separated from station B by this cloud of interconnect, just keep pumping data into the network as fast as it is producing it, and expect the interconnect or the station at the other end to absorb it at whatever rate it's sending? And the answer is probably not, and there needs to be some method for doing flow control, for letting A know that it can't keep sending to B, or that A know that it can't keep sending to the interconnect, either because B is clogged or because the interconnect is congested. And there are lots of complicated schemes for doing that that vary from network to network. Store and forward versus wormhole routing. Sometimes you have station A, which is going through an intermediate switching node to go to an intermediate switching node to go to an intermediate switching node to go to B, and it's trying to get a packet or a piece of information or a data word that's being stored into memory. B might be memory, from A to B. How does it do it? The simple way to do it is to first transfer that piece of information to switching node 1. And then when it's there, you transfer it to switching node 2. And then after it's there, you transfer it to switching node 3. And then when it's there, you transfer it to B. And that's the kind of store and forward scheme, where you've stored it in S1, and then you stored it in S2, and then you stored it in S3. That has reasonable bandwidth. You can get things flowing through this pipeline pretty fast. But it has terrible latency, because it takes 3 separate transfers, or maybe 4 separate transfers, before B actually gets to see the data. Another scheme is to do so-called wormhole or cut-through routing, where you don't wait for this packet to get into S1 before you start sending it to S2. Let's say it's a disk sector that you're sending from the disk to memory. You send the first few bytes to S1. Before all of it's in S1, you begin sending whatever is in S1 out to S2. So basically you decrease the latency by starting the transfer as soon as the data is in. Obviously there are complications which we may or may not get to talk about doing that, but in general wormhole routing is a good thing because it tends to reduce the latency of getting information from one node to the other. And as always, the two numbers we're always concerned with for performance are latency and bandwidth. And as always, they are not necessarily related to each other. You can increase one and decrease the other. There are other topics that designers or users of networks obviously need to be concerned about. One is redundancy. In a single computer, if the CPU breaks, well, the CPU breaks, and you get it fixed. If you've got a shared multiprocessor built out of 1,000 processors, and one of them breaks, you can't afford to have the whole machine break, because the probability of at least one being broken is too high. So you've got to have some way of having redundancy in the switching fabric or in the processing nodes. You've got to be able to reconfigure on the fly so that you can change the path by which information travels through the network, or change the computers on which parts of this problem are being executed without bringing down the whole system. And then there are sort of non-technical issues of standardization and choosing the appropriate technology for doing these multiprocessors so that, number one, it works okay, and number two, that it's going to work 2 years from now because people continue to make and use that technology. And unfortunately, those are also sometimes separate decisions. Okay. Focusing back for a second on these tightly coupled multiprocessors, basically there are 2 ways you can build them. One way is that you can build them really like separate computers, where each computer has a separate address space, and they can talk to each other, but they talk to each other by mechanisms which look just like the software mechanisms used for networks, local area, wide area networks. You pass messages or packets between the two pieces of memory. You can implement a remote procedure call where, from the software programmer's point of view, it looks like you're executing a function call, but in fact that function call is going over to the other CPU and gets packaged up and sent as a bunch of information over to the other CPU and over to its memory. But a more interesting and more challenging way of building these multiprocessors is in fact to do hardware sharing and make multiple CPUs all access the same memory as if it was one memory, even in the case where, in fact, it's not one memory. In the left diagram, it shows CPUs with their separate caches, all accessing a single main memory. And in fact, they all have the same latency and bandwidth characteristics getting to that main memory. That's the so-called uniform memory access model. But a more fun way to design the system is this way, where each CPU, in addition to having its own cache, also has its own memory and I/O devices, which are accessible by other CPUs. So this CPU, well, certainly accesses its private cache, may access its private memory, but may also go through the interconnect to access a piece of memory that's over here. After all, it's one big piece of memory. It probably is one uniform address space. So if it does a load instruction from data that happens to be in the cache, it gets it from there. If it happens to be in its private memory, it gets it from there. If it happens to be in somebody else's memory, which is across the room or across the country, it gets it from that other memory. And it's still just a load instruction. So the software, to first order, doesn't care. Now, this is a very non-uniform memory access, because obviously the time delay will depend on where that memory happens to be. But it's still a simple software model that allows a program running in this CPU to view all of these memories as if they were one gigantic memory space that is private to itself, that just in reality happens to be spread across multiple processors. Now, one of the main issues in building a processor like this is what to do about the caches. After all, if this CPU reads a piece of data out of one of these memories and puts it in its cache, and some other, and in worst case modifies it, so piece of memory just became modified, and let's say that it's not a write-through cache, so the only place that this modified information is in its private cache. What happens when this CPU reads that data? Well, first question is it in its cache? Let's say it's not. Even so, it's going to go to the memory in which that data was originally located, bring it into its cache, but it now has the old value of that data, even though it's been modified in the first CPU's cache. This whole problem is called the problem of cache consistency, or coherency, of keeping the data in these caches consistent, and next time we will talk about how to solve that problem.